I want to say the traditional Ignite format, I think, is one of the most difficult talks to give. I think we're a little loose on the rules today, but it's 5 minutes, 20 slides, auto-advancing, and I did one at South by Southwest a couple years ago. I think I practiced it the entire day before, and I went up and nailed it, and they recorded it and lost the recording, so I don't even know how I did. It was great. Anyway, I'm Jason Hibbets. I'm part of the All Things Open team. I work on our We Love Open Source blog. So if you go to the allthingsopen.org website, you'll see articles there. We accept guest contributions. We accept guest posts. We're looking for more authors. Really excited about it. We kickstarted the We Love Open Source blog in April of last year. We're now able to publish 5 articles a week. And we're doing some great stuff with the We Love Open Source podcast. So you've seen us in the studio, we're interviewing some of our speakers, and all of that content will be on our YouTube channel and eventually on We Love Open Source. So because these are Ignite talks, we're gonna do lightning introductions. And our first speaker is Kevin Blanco from AppSmith. Please welcome.
All right, how's everyone doing? Good? The energy on this area is amazing. My first time in North Carolina, I flew all the way from Costa Rica. And you might be wondering, why is Kevin wearing sunglasses indoors? You're probably going to tell the person next to you, oh my God, we're stuck with the weirdo. But the case is, there is a reason why I'm wearing sunglasses, but I'll tell you the reason at the end. Normally, people get very excited when I put this slide on because they think I'm going to be giving away a kiss among the audience. Don't be excited about it. KISS is actually a principle I rule my life by, which is keep it simple, stupid. And believe me, it helped me a lot in my career because, unfortunately, engineers love to make things complex. And this principle helps a lot when it comes to working with enterprises and people that don't get engineering. Now, do you know one thing that is not KISS principle? The noise around AI right now. If we see on LinkedIn every week there's a new announcement around a new product about AI, there's a new model with new benchmarks, there's a new startup from the United States, China, you name it, about AI. And if for us, who are at the forefront of AI, building AI solutions, it's hard to keep up with it. Now picture a business owner who doesn't have the technical background, yet it sees the value of implementing AI. It's probably as confusing as the image you're looking at right now on the screen. So let's talk about the 2 things that I believe are making things complex for enterprises to adopt AI. The first one is the data mess. We're talking about enterprises who has legacy databases, structured and unstructured data on multiple places, and you're going to tell them that they have to bring all of that data and fix it to bring it to their models and do fine-tuning. Enterprises don't have the chance to do that. The other thing I believe is a problem is there's just too many SaaS applications. Like enterprises have to switch between maybe 10 different apps among their day and switch between them maybe 30 times per day. Good luck adding a new app, maybe a new AI platform to that suitcase of apps they have to use every day. I mean, I cringe every time I hear Salesforce. Am I the only one? Dude, it's complex. So, given that, that's why Gartner came with this number, which for me is pretty shocking, that companies take around 8 months to leverage an AI project, and 52% of them, unfortunately, fail. And I think it's primarily because of the 2 things that I mentioned right now. The big data mess, or not mess, but just the amount of data they have, and the amount of tools that they have to switch. So I believe that for an AI solution to be actually useful for enterprises, they have to meet them where they're at, don't have to change their data structures at all. And second, it has to be embeddable in the platforms and the tools that are at already. So I'm going to show you a very simple RAG implementation. I guess we'll hear about RAG already a lot of times, so I'm not going to explain what RAG is. Let's just put it superpowers for your LLMs. That is going to have access to certain data points and be able to retrieve that in a certain scenario. That's, for me, what RAG is. I believe you've probably heard about RAG, so I'm not going to spend too much time on that. So here what we have right now is looking at a dashboard, and I'm gonna drag and drop a chat widget. This chat widget, I'm gonna first of all let them know what I wanted to do. I'm gonna give it a prompt. This is what you're gonna be helping me with. And I'm gonna bring a data point. The first data point I'm gonna bring is my knowledge base. All enterprises have files, PDF files, Excel files, so I'm gonna bring them over. So my RAG pipeline is going to be available to access that data. Then I'm going to access my docs. I already have living docs in my public documentation. My team spent a lot of time on that. So let's bring the docs.appsme.com to the table. And just like that, this RAG pipeline is going to help to bring and web scrape all of that content that I have on my docs. So with those two already trained, let me just go and deploy this RAG pipeline and this AI chat, and I'm gonna ask a question that I got about a MongoDB error that somebody is getting when trying to install AppSmith. And just like that, it's gonna give me the answer from those data sources, but giving me the citations of where the LLM exactly grabbed that data from the documentation, from the docs. Now, citations are extremely powerful because it's grounding the responses. That's the beauty of RAG. Now I'm gonna give it another question. Turns out somebody's asking about the one-click project being delayed. Now this is a very specific product question that is not accessible in the outside or to LLM, and it's gonna tell me, I don't know about that. It's gonna be grounding, again, on real data. So let's go back. Let's bring Notion, because Notion is where we keep our product information. So I'm just going to, again, bring Notion to my data pipeline. I'm going to give it access to the right pages that I wanted from my Notion documentation. And just like that, I'm going to redeploy after it's trained on these particular pages from my Notion documentation. And now that it's trained on that, let's redeploy the chat widget. Click deploy. And now let's ask again about why the one-click project is being delayed. And that's on the Notion documentation. So now it's telling me there were some design problems, some execution, you know how that goes with enterprises building dashboards. And again, it's giving me the right citation of where it got this information. Now this is extremely powerful because it just took us 3 minutes to build an entire chat solution with RAG pipeline, giving it grounded solutions without hallucinating. Let's do something else. I think it's very powerful what we just did, but let's bring 3 other data sources. The first one is Zendesk. Turns out that I have all of my customer support questions happening on that Zendesk. So I'm just going to import Zendesk as a new pipeline to my RAG implementation. Also, I'm going to bring Salesforce. That's where all of our sales information is, all of our customers, all of the contract information. So again, I authenticate, Salesforce is on. And now let's connect to also Confluence, because Jira is where I manage all of our tickets. So I'm going to integrate with Atlassian as well and redeploy this chat widget. Now we have 3 more data sources compared to the first one that we got, which was 3. Now we have 6 data sources. And to see the true power of this, I'm going to install the AppSmith agent, which is an embeddable agent. And this is where I was talking about meeting the enterprises where they're at, because they don't need another tab. They don't need another place to go. They wanted to have it right where they're at. So I installed the agent. I'm going to embed this application in the agent. And I'm going to tell it in the configuration that this agent is going to be available when somebody is on Zendesk. I can do as many mappings as I want. So inside Zendesk, when I get a customer support inquiry, I just open the chat and I ask a question. And I'm going to be asking about, hey, what's the problem with this ticket? And just put the link of the ticket. And the RAG pipeline, since it has access to it, is going to bring all the information that got from the knowledge base, from the customer support contract on Salesforce, and it's going to be giving me a direction as a customer support agent. Hey, this customer seems to have the right contract, since that everything is in place. So for me, that looks like a bug. So I recommend that you create a bug ticket in your Jira system. So great, I say, all right, I'm going to create a new Jira ticket. It prompts me with the information that it grabbed from the ticket, that it grabbed from the knowledge base, and it's going to allow me to create a Jira ticket without leaving Zendesk, without going to another tool. So I tell it, yes, that ticket looks good behind the scenes. It's going to let the team know via Slack that there is this new ticket. Human in the loop. This is for me the most extreme powerful when it comes to agents. Not everything has to be automated. And last thing, it proposed me an answer to reply back on the ticket, and I can just hit send reply. It's going to send that directly to the ticket, letting the person know that we understood that this is a problem in our system, that a ticket has been created, and that they can see the progress on the link on the ticket. This, for me, goes back to the KISS principle. It was fast. It was easy. An enterprise can bring multiple data sources to a RAG pipeline in just seconds. So that's what AppSmith agents are. AppSmith is a low-code platform that has been on the market for more than 6 years, helping enterprises build internal tools and dashboards. And now, with that same principle of data privacy, self-hosting, running on-premise or on your own VPC, you can have your enterprise agents running privately within the same VPC and your same private network, having access to all of these tools. I'm Kevin Blanco, Senior Developer Relations Advocate at AppSmith. If you scan that QR code, it's going to take you to my LinkedIn profile, and I would like to have a conversation about this with you. The reason why I'm wearing sunglasses today is because I've seen the future, and it looks so bright.
Great job, Kevin. Thanks so much. Brandon's going to get his slides up, but we've got people still trying to come in. So if you're on the edge, we're going to do a stretch break. If you want to stand up, move to the middle, allow some people to move on in. That would be great. Got my good friend Brandon Mathis here, working with this dot now. And you ready for it? Ready to go?
Oh, nice.
He emails us and says, my slides are a website. And I said, of course they are, Brandon.
Yeah.
Here you go.
So I can't do anything without adding like a little bit of engineering flair to it. By the way, my name is Brandon Mathis. I'm engineering lead at This.Labs. We're a consulting agency that specializes in JavaScript development for web and mobile applications across a variety of industries. And what my Ignite talk is going to be about today is kind of just a bit of, thinking around like evolution versus revolution when it comes to coding with AI. Are we in a revolutionary time, or are we in another evolution of technology? So, to talk about the history of computing really is a lot, I think. So I'm going to go very quickly here, and I'm going to set myself a stopwatch, and I'm going to be done in about 7 minutes. 1980s, the United States had a major issue when it came to tabulating the census. It took 2 years to count up the totals. Too much counting took too long. They asked a guy by the name of Herman Hollerith to create a machine that can make this faster, and he created what was called the Hollerith tabulator, which used these punch cards. Oh, are we falling off? Check 1, 2, AV.
Your other picture was up.
Mm-hmm. Uh-oh. I'm seeing black right now. Did I step on a cord, maybe?
HDMI.
Oh.
It's this right here.
Do not touch that cord right there. Now everything's black. Oh, fantastic. Okay. By the way, if you want to follow along at any time, just scan the QR code at the top of these slides. This is running on a Next.js website hosted on Vercel, so you can kind of stop on an image that you want. But to go back to what we were talking about, we were talking about tabulator computers. These things use punch cards punched by real humans to record and store data and display it and calculate and summarize it for the United States Census, and it solved a critical problem. It took 10 years to complete a census. With this machine, it took just 6 months. Someone was like, oh my God, I should sell this to insurance companies. So this is kind of like the first computer ever created, and you would program this thing via like a plug board, which is an absolutely crazy concept. You would load data in via punch cards, and this thing was completely electromechanical. You had to be a specialized individual to be able to dive into this thing and diagnose issues that were going wrong. Well, kind of happening at the same time as these things called vacuum tubes are getting created, and the information era was sort of being born. And information theory was this concept of storing data as ones and zeros. And a woman by the name of Grace Hopper said, you know what? Let's put the code inside of the computer. So, a few people were like, okay, that's interesting, but let's kind of get started with a few of these major devices. So we have the ENIAC computer gets created in 1946. In the early 1940s, 6 key women are selected from the mathematics department at the University of Pennsylvania to do some of the first programming ever. They created concepts like breakpoints. They created concepts like debugging and some of the fundamentals that we use here today. And this computer eventually evolves into the IBM 604 patch panel computer. You program this by like wires, y'all. Could you imagine writing code like this, loading it into a machine? Like, I mean, this is crazy to think about. This is what a programmer looked like in 1995, all right? This is your company repo. This is where you kept all of your code, all right? Each one of those are patchboard panels. You load them into the machine. There's DevOps working late at night, deploying your code into the machine. I mean, come on, look at this. Diagnosing, for real? Come on, how am I gonna find an error in this? This is documentation. What? Come on, I can't it's too much, it's very complicated. And you know, Grace Hopper, she's like, for real. Let's put the code inside the computer. And we had one of the first major revolutions, in my opinion, in computer programming, which is the ability to modify code directly inside of a computer. You could do this on the UNIVAC, released late in the 1950s. It still used vacuum tubes. It used a very interesting system for storing memory. It used what was called a UNIVAC Mercury delay line memory system. This was a giant transistor surrounded by 8 glass mercury-filled tubes, and it would store information by sending sound waves through these mercury tubes, and it would bounce back and forth on the tube. And eventually someone said, that mercury stuff is kind of crazy, y'all. Let's not do that. They created the IBM 704. And things kind of mostly stay the same with the 704. Languages like Lisp, Fortran, Algol 20 really rise in popularity. We're kind of still in the 50s here, 1955. This was a common IDE environment for you, all right? 1950s, punch cards still very prevalent. You did never want to drop these things. You dropped them on the ground and they became disorganized, you had a disaster. People would actually strike them diagonally with lines in case they did drop them on the ground. Maybe you could reorder them again by looking at the diagonal line on the side. Best of luck to you, right? Here's some programmers in an open office, 1950s. Pair programming, late 1950s. You would write code and then you would verify it on another machine. You had to have 2 people doing this stuff. This stayed pretty constant all the way up to 1957. IBM comes out with the 709, which is a totally vacuum tube powered computer, but then transistors come onto the market. And we have the IBM 7090, 1959. Coming into the 60s, what does the 60s remind everybody of, right? The space race, okay? NASA had a mandate from the president to send a man to the moon, and we had to go bigger, we had to go faster, we had to calculate things at rapid pace. And we went from the Redstone 3 rocket, which sent the first man into orbit around the Earth, all the way up to the Saturn V. Size comparison for those of y'all that need to understand what a monumental engineering lift this was. We needed computers that could go really fast, and that's where the IBM System 360 comes into play, 1964. This computing system was used pretty pervasively through NASA, introduced the first ever unified architecture where you could upgrade things piece by piece. You know, beforehand, if you wrote code for a machine, it only ran on that machine, period. If you got a new one for the next year, you had to rewrite all your software. That was a disaster for business owners. The IBM 1130 console, this was sort of like an interactive development environment now. You actually, for the first time, got feedback from the computer. You weren't running things in batch. You could send an instruction, and you could get information back. 1965, this happened. That was like revolutionary at the time. Everything was done batch. You had to wait overnight for your code to run. This is kind of what an office environment looked like 1965, y'all. A similar computer here, the PDP-7, this is what Unix was developed on. That is what it was coded on. That is a teletype machine. It's a console that is completely, the PDP mainframe, but that console, it prints out paper. Paper. It's like you opened up your JavaScript console in your browser and imagine your printer started running. Oh my God. I need to see the output now. Why is it taking so long? Everything's electromechanical. All right. This is what Unix and the C programming language were essentially built on. Dennis Ritchie and the group, and along with a few other critical languages. COBOL, checking my time here, we're looking good. BASIC, a couple examples of BASIC. Lisp at the same time, 1960s, Lisp is coming out. list-oriented style syntax that was really revolutionary for the time because it was used to create the first ever AI chatbot called Eliza. This was like breakthrough, y'all. 1964, we're doing the first ever AI chatbot. We've been working on this AI stuff for a while. Again, this is what we're using, right? We really needed a revolution bad. We were printing out punch paper tape. You'd maybe tape it together and run it through the machine again too. You would call that a loop. You tape one in together, literally run through the machine multiple times so the code could rerun. But the big revolution sort of breaks place here with microprocessors, and this is where I'm gonna go really quick, because when the 8008 processor came out, the semiconductor manufacturing industry kicked into high gear, and we could finally make these wafers in the 1970s. You did this by hand. You carried them through the manufacturing plant by hand. You operated the lithography device by hand, but we created some crazy computers. This was just a typewriter, 1973. It didn't do anything. You could just type on your screen. The Altair, some of y'all may be familiar with this. Someone was like, yeah, that's a cool computer, but the way you coded it was you flipped these switches. And you wrote everything line by flipping switches like this. Someone said, nah, we need a revolution, all right? And they plugged it up to a TV and a keyboard, and stuff really kicks into high gear from there. Lots of computers explode outwards. Sorry, that might have been a bit too fast. But I mean, this was like, the TRS-80 was like the peak in 1977. The Apple II, 1978. The Apple II with a monitor. And just 15 years ago, that was the peak of computing at the time. All right. Continue to go forward. 1980s, we have the Commodore, Apple Lisa, Macintosh comes flying out. 12 years ago before that, when the Lisa and the Amiga came out in 1987, that was only 12 years ago. Continuing forward with lightning pace modems. This is how we used to connect to the internet. What the heck? All right, you put it on that? What? Seriously? Whoa. Major revolution happens. We're able to plug modems into computers, and we birth forth kind of like the beginnings of the internet. BBS systems where you could share code, share games, communicate with other people. We used to send code to people printed off like that, and that's you programmed it in by typing it by hand. Now I could send you a floppy disk. We had evolutions in GUIs. This was a GUI from 1983. Then check out Windows 1. Amiga Workbench in 1984. This is all the 80s. This happened in a decade. We went all the way to that. From like that. That's crazy to me. The 90s, I'm kind of getting more into the territory of stuff it is that y'all are familiar with. Like, you know, the early release of Linux, Python coming out, Windows 3.2, this was my home computer in the beautiful hot dog theme that you could apply to Windows 3.1. I loved that one. The Amiga 1200 was very popular. Windows NT released 1993. The Mosaic Internet Browser, 93 and 94 come out. And Java in 1995. And 1995 kicked things into high gear. All of these languages came out. Windows 95 came out in 1995. Did y'all know that? That's crazy, right? This dude sold us an operating system 1995, 20 years ago. He saw that, right? 20 years. You know, continuing on into 1996 and into the early 2000s, I always kind of like to stop on this slide. 1998, Google looked like this, all right? Salesforce looked like this, 1999, Salesforce.com. What? First SaaS application. Bunch of new languages start to burst forth in the early 2000s. The Agile Manifesto is founded 2001. Multi-core processors created 2001. Windows XP releases in 2001. And a bunch of languages burst forth on XP. That doesn't look right. Yeah, that looks a lot better. Yeah, that's nice. Ubuntu Breezy Badger. This was like my daily driver operating system, 2005. Amazon AWS, 2006. The NVIDIA CUDA, you could actually write compute level instructions to a GPU, and you didn't have to use like obscure vertex shader oriented programming libraries to do compute on a GPU. Major smartphone evolution flies through. Maybe not that much of an evolution, but that was an evolution. That was a major deal. And then Stack Overflow, 2008, GitHub 2008, Node.js, Go. This guy was trying to sell us an operating system 14 years prior to when Node.js came out. It's Windows 95. Now, kind of launching forward, we're in the current era. Y'all remember the browser wars of 2013? I do. Or the JS wars, sorry. The browser wars was before that time. Rust and Swift released 2015. TensorFlow and PyTorch now, like, you know, PhD people, master's level people, anyone could build a machine learning system. AlphaGo gets released. We finally have quantum computers explode forth in 2019. And now that kind of brings us to today, 2022. We're coding with AI. And I want to ask you now, do you think we're in an evolution right now or a revolution? Because in 2026, that would have been 80 years ago. Programming computers, punching them in with plug boards. Put some thought towards that. That's my talk, y'all. This entire slide deck was built in Next.js with AI. I used Anthropic. You can scan the QR code at the top to view the GitHub repo. I spent $44 in prompting to write this entire website. I didn't write a single line of code myself. Do not even ask me about the carbon emissions that might have been generated from doing this, because it's like the equivalent of driving a car like 34 miles or something like that. But we're getting better, but I figured just a little openness would be nice here. But that's why I taught y'all. Thanks.
All right, thanks, Brandon. He's going to help get the next pair of slides up. All right, that was great. How many total pictures was that? Do we know?
150.
150, if you're curious. All right, our next speaker, Ash, come on up. Our next speaker is Ash Tewari from Applied Information Sciences. Please give him a warm welcome.
Which one is yours?
That one? Nope.
Oh, this one.
Oh, it's right on. Cool.
Okay. Wow, there's no toolbar at the top. What does that even mean? That should be good now.
Yep, sounds good. Thank you.
Be really careful with that port. Right?
Yeah, don't touch that.
No touch.
Don't touch the cord. Let's get it up for Ash one more time.
Thanks, everyone. Thanks for being here. My name is Ash Tewari, and I work at Applied Information Sciences. I solve problems, mostly using software, either writing software or creating software or putting teams together to create software. I'm going to talk to you about an application, open source application that I built about a year ago. I wanted to see what's inside a vector database, so I started putting this together and just built on top of it to just trying to understand how things are working when you're putting together a RAG application. And you thought we were going to be done with talking about RAG, right? Not yet. So I'm going to make some very specific points about a few things in these areas: embedding models, chunking, strategies, indexing, some optimizations that you will need to do once you get beyond naive RAG and eval. This is how the application is built. It's called Bookshelf. It's using Streamlit, Llama Index, ChromaDB as the database, LangChain. I'm using LangChain really just as an abstraction to the models. There are other better ways to do it now. Deep eval and pandas. There are a lot of different ways that RAG is explained. You can see that up there. A lot of different ways to explain the concepts from different point of views. This one here is an example of workflow. If you look at the workflow in the middle, going from top to bottom, that's indexing workflow, ingestion, some people call it ingestion, right? And there's a workflow at the bottom going across. That's where you're doing retrieval and generation. The main thing to think about here or know is that indexing is done at a different time than retrieval and generation. These are two separate things that happen. It might seem like when you are getting started with it that it's one flow, but it's not, right? Usually, your indexing is done before you can ask any questions. And you saw in that workflow, the indexing workflow, it's using a embedding model to create the vector indexes, right? And then there is a inference model that you use to generate the responses to your questions. So you will see that later that the inference model is actually not just used in the generation. When you get to an advanced RAG solution, the inference model is actually used before the retrieval also. And I'll show you that in a second. So there are basically two different models, right? There is an embedding model, there is an inference model. They have nothing to do with each other, right? You can use an open source embedding model with OpenAI's inference model, like, or vice versa. They have nothing to do with each other, except the embedding model. Now we know that it's used to create the vector indexes, right? But it's also used whenever you need to match the indexes. When you are doing a query, you need to do a similarity search, which goes to the vector database. And both of those operations they need to use the same embedding model. So once you have a vector database and you're trying to use that in your solution, right? When you're trying to use that same vector database in your solution, you have to know which embedding model to use. So how do you do that? You know, if you, in a large application, you may not even know what's in a vector database. So how will you know which embedding model to use? You have to think about that, right? So the way I did it in Bookshelf is by actually writing the embedding model into the ChromaDB as metadata, basically. So when I'm trying to do the matching, I actually check to see the database metadata to see which embedding model was used to create that. So that's how you can match it up in the future. So. All right, so the embeddings that are generated, right, they have to match with the embeddings that you use to vectorize the query. And this is what happens if they don't match. So this is an indication that you're trying to do something that's not allowed. You do have to sometimes actually store multiple embeddings in the same database. There might be a reason why you want to do that. Sometimes it's cost, sometimes it's performance, sometimes it's the use case as well, right? So sometimes it's embedding models, just like your inference models. They are sometimes fine-tuned for scenarios for different domains, like medical, legal. There are specialized embedding models that they do that. So sometimes you have to basically embed the same data using different embedding models, and they have to go in the same. You need to have access to both multiple embeddings, and the databases that allow you to do that. ChromaDB doesn't allow you to do that. Like if you want to put the two embeddings in the same row, you cannot do that. VV8 allows you to do that. PG vector extension to the Postgres also allows you to do that. How much time do I have? Oh. All right, I'll skip ahead a little bit. So the embedding models, let me just skip forward so I can go through this a little bit faster. So when you're looking at embedding models, you want to look at the MTEB data to see where the embedding models actually stands. In a simple RAG, in what's called a naive RAG, right, you have retrieval and you have generation. That's probably what you have heard today or yesterday. But once you get to applications that require more precision, you will, do some optimizations before the retrieval and after the retrieval, and even after the generation. So in the bookshelf, these are some of the optimizations that are available, like chunking strategies. You can token text is the simple one, sentence splitter, semantic splitter, and the hierarchical node parser, right? So semantic splitter, actually, this happens before the retrieval, right? But it's using a language model to do this. Hierarchical node splitter, basically, it allows you to create different chunks, different size chunks. So you can create chunks at 256 size, 512, 1024, and it allows you to basically do a retrieval from a small chunk, and then you can basically use this in conjunction with something that's coming up to finally retrieve something, retrieve a context that's actually larger than the chunk that it's matching on. And in the application, in Bookshelf, you can play around with all these different configurations, different parameters. The next one up is enrichment with metadata. This is also, you can do that also in this Bookshelf. This is basically a tool to learn about RAG, on how to implement it. So it has a lot of switches that you can use to learn about exactly how to implement it. This is auto-merging retriever, is the other side of the hierarchical node parser. You can use this to finally implement the technique where you can match with a smaller node, smaller vector, and then combine it together automatically to bring up a more relevant, larger context for inference. And re-ranker is another optimization that you can do post-retrieval. In Bookshelf, you can do two types. You can use two types of re-ranker models, a cross-encoder and the BGE re-ranker. You can also use a custom model also, but it has to belong to one of these categories. So I'm going to wrap up. So, and these re-ranking models and the Hugging Face embedding models, you can run all of them locally on your machine. You don't have to go outside. Inference models also, if you can run them on your machine using Olama, it's all, you can hook that up in this application so you can do everything locally. So when you're running it locally, this is how you want your utilization to look like on your machine. If your CUDA is not being used, you will feel it. It will be very slow. Your machine will spin. This is how you can find out if CUDA is actually available in your environment. And this is what you want to do to enable, to make sure that the code that's running is actually running on your GPU. So there's a link on top of this, which you can use to generate a command that you have to run within the Python environment, your Conda environment, for example. So this actually sets it up in your local environment for GPU use. All right, so once you do that, it looks better, and I'm going to skip over eval. We've heard enough about that today. All right, and that wraps it up. It's open source. It's on GitHub, and I invite you to actually play around with it. You can use this as your own learning tool and have fun with it. Thanks.
Appreciate it. one moment while we transition here. How do I get out of the presentation? Oh, exit and show. How about that? I don't have the mouse. Where's the mouse?
It's only other window on the lobby nowadays.
What? I don't know how to do this. Sorry about this. All right. All right, our next speaker, that's not it. Is that all yours? Okay, I was like, that's not the name of the speaker. That's cool. How do we want to start these? Where did it go? Slideshow. Okay, our next speaker, pardon me, here's your clicker.
Okay, thanks.
All right. Our next speaker is Keith Bergelt from the Open Invention Network, and we'll hand it right over.
Great, thanks very much.
Please welcome to the stage.
Appreciate it. I'm cognizant of time, and I appreciate always the opportunity to speak at All Things Open events. Todd has been doing this and doing a masterful job for years. Mark did a great job this year riding shotgun, and for something completely different, what I do is safeguard the community so that people can make choices. Customers can make choices about what they want to use, whether they want to use open or proprietary. 25 years ago, IBM was very concerned about what the future was going to look like. There wasn't as much adoption as they would like. And for several years, they toyed with a number of different approaches. Then they got together with SUSE and Red Hat, and they decided that they would actually put lots of money in, $20 billion a piece, and they had 6 companies, IBM, Red Hat, at the time Novell, where SUSE was housed, Sony, NEC, and Philips. Toyota and Google joined later. These companies all contributed significant amounts of money to provide for freedom of action and freedom to operate in open source. And for the last 18 years, I've been stewarding this organization. It's now the largest patent cross-licensing community, so patent non-aggression community in the history of the tech space. There are over 3 million patents that are encumbered, and it runs basically by saying where we collaborate, we want to be in a situation where we can continue to collaborate openly and freely, and where we compete, but we're not going to allow patents to get in the way of the collaborative relationships that exist in the core of open source technology. The modality is really what we're protecting of open collaboration, so that 1 + 1 + 1 doesn't equal 3, it equals 6 or 10 or 20 when we bring smart people together and allow them to collaborate across the world and across sectors. And so my job is a wonderful one because I go around and talk to people all around the world about participating in this community. When I had this slide set put together by my team, what we do typically for any emerging technology, we did this for the cloud when OpenStack first kind of came on the scene, and we've done it related to CNCF, as well as we look at who owns the most important patents in the space. Where are those patents and what are they doing with them? And we try and bring the companies into our community so that we can ring-fence their patents that are core fundamental technologies that everybody wants to use and build on. And so we try to make sure that those companies are a priority. And when we look at the companies that, this is just a kind of from a geography standpoint, this is anybody who's in this space kind of understands that the US and China are the leaders in terms of patenting around AI, and then you have South Korea and Japan, and then you have other countries that are trying to catch up. What we look at are patents that are granted, and then we look at patents applications, because the latter shows us the directionality of who's actually getting on board to actually start doing a lot of filings. Some companies, we look down the list and we say which companies are are living on the wrong side of history, because some of these companies are actually going to start to sell their patents to non-practicing entities, which are patent trolls. That's a concern for us. Originally, when OIN was formed, we were mainly focused on a monolithic threat. There were few operating companies that were concerning, but none more than Microsoft. Microsoft 7 years ago became a member of our community and pledged its patent portfolio to support open source, and really went from the rhetoric of saying that they loved Linux to actually showing that they loved Linux by participating in this, which is a litmus test of authenticity for companies. And so we have most of the major companies of the world, most of the most significant patent holding companies of the world that participate in our community and recognize that collaboration on intellectual property is also important as a parallel to what we do in technology collaboration. And so you look at the companies here, of the 10 companies, the largest 10 companies in terms of AI assets, 7 of those companies are in our community. We look at the other 3 quite carefully and look to bring them in. That's kind of how it's worked for cloud. That's how it works for many different technologies, and that's how it's working for AI. As we look to expand the scope of our license, this is a very weird organization in that there's never been a successful license in the history of the patent world where a licensor, OIN, has the ability to expand the scope of the license without approval of the licensee. And it's a strange thing, but the trust that people have in what our commitment to doing the right thing, to not overly expanding the scope of the definition that we use to create the cross-license zone, and our belief that innovation is not just coming from the patent world. Innovation comes from open source, and increasingly open source is becoming the environment through which innovation occurs in the more significant way and more rapidly developed. And so these are just for flash purposes to kind of show you this is applications. And if you look at these, you'll see that there are some changes in terms of who's involved in new applications. You see NVIDIA on this list. You didn't see them on the granted list. You see Intel on this list. You didn't see them on the granted list earlier. And so we look at companies and we try and bring them all in to our community so that we're creating this opportunity for people to make good choices about what they ultimately want to build their platforms around. And so if this is a call to action, without belaboring the point, we're always here running in the background, looking to be able to deal with patent risk mitigation issues. If someone's approaching you with patents and asserting those patents and they're open source related, come to us. That's what our job is, to deal with aggression, to be able to create a placid situation and reduce friction in the community. And so no one can escape the fact that we're all participating in open source now. There's no silo to hide in. And as a result, we just continue to expand the scope every 2 years of the Linux system definition, which is really that scoping of the cross-license zone. Anyone who has functionality that they think is important, that they would like us to consider to include in the scope of the license, this is your opportunity, because we're right now actively developing the next, which is the 13th table, the 13th expansion of the scope of the license. We would like to have nominations. You don't have to have any status. You don't have to have given us any money. In fact, our license is completely free. Join, sign the ClickWrap license on the website and become a part of the community. Be protected, as well as nominate things that you think are important, technology that you think is important that we should be incorporating. We want we have an open dialogue with companies all over the world. We'd like to expand that scope and make sure that communities like this are aware that we are open for business and looking to help mitigate patent risk and reduce friction. Thanks very much.
Thank you, Keith. All right, Nathan's going to help me transition slides. The next topic is really interesting. It's on the screen. That's why I had trouble with it. Yeah. Anyway, actually, Keith, I actually have at my time at Red Hat, I had a couple of patents, and I thought it was a really interesting process to go through. It made you kind of like, it forced me to do more systems thinking and like at a high level, and it was really interesting. So our next speaker is Wade Moore, and I'm from Observe Inc., and I'm really excited about the topic because I've been learning a lot about it this week. Welcome to the stage.
Hey, thank you so much, Jason. The clicker right here. Great. Hello, ATO! Thank you so much for coming out here today. My name is Wade Moore. I'm a solutions architect at Observe Inc. Observe is an observability provider, go figure. And my job is to work with partners to help manage and make sense of all of their data. So what does this have to do with AI? Well, the goal for the next 5 minutes is to give you all a crystal clear vision into what the next generation of observability is going to look like. And so we'll answer the question, why observability in AI? We'll look at AI runbooks and investigators, and then we'll take a look and review what agentic AI and RAG solutions mean for observability. So without further ado, why observability in AI? If you see this depiction right here, you'll see the market size of the observability market in dollars and the growth projected over the next 10 years. Today is a $2 billion market, projected to 3x, to triple over the next 10 years. And this simply means there is plenty of capital, AKA money, for fueling innovation. And so look forward to that coming, along with enormous amounts of data associated with observability. I work with a lot of heavy hitter clients. The one most notable that I can publicly talk about is Capital One. They send over 100 terabytes of data per day, and that's not nearly the full picture. Not to mention they spend tens of millions of dollars per year on observability solutions. So the seeds of innovation are in the ground. Another worthwhile mention here, especially for our folks at All Things Open, some really positive trends in regards to the open source community. The observability market has rallied behind the open telemetry standard for logs, metrics, and traces. And most recently, or more recently, they have established more headway into making Apache Iceberg the open standard for underlying data lake tables. And this means a lot more innovation is going to come from these open practices, empowering more and more vendors and the open source community to make innovations. So let's get into the good stuff. Start off with the best thing first. I present to you the AI Investigator. This is not your average chatbot, worlds apart from what we have out there today. Now you can explore your data without requiring tribal knowledge. Now you can collaborate with your team members in real time. And you can now also automatically capture your investigation step by step so that you can return to it later. This is a quick peek of the AI Investigator from Observe, one of, if not the first, to hit the market, but we fully expect other observability providers to quickly follow suit. This will be the new way to interact with your observability data. And so moving right along for the sake of time, I want to open up the hood and look at some of the underlying tech empowering what we can achieve there with the Investigator. Starting out with the alerts we all know and love. Of course, looking for app errors or issues in the metrics, but now we can include runbooks. Leveraging the same capabilities you saw in the Investigator, we can define the next steps to take in our investigation. And what you see here is quite literally the configuration. No JSON, no complicated tribal knowledge, just typing out what you'd like to see, and now generative AI can take that, specifically an orchestration AI agent, which is going to feed into other AI agents. As of right now, initially, these agents are just going to be specialized, understanding their category of data best to help recommend solutions. But eventually, these recommendations will turn into actions and provide automatic remedies to your Kubernetes clusters, GitHub repos, Jira tasks, and of course, going back to our observability platform using observability agents. And so last but not least, I want to mention what RAG means for observability, just listing out the sources that are included today to help provide context to user queries. As you might expect, we got public and internal documentation, online web forums, blog posts, anything you can get your hands on. And what I also thought was notable here, particularly for observability, is using code in the documentation in code. particularly for the query languages, proprietary languages that observability providers support, and all of them at this point have some form of a copilot attached to them. And the question I get from all of my clients all the time is, when can I start using my data inside of these AI solutions? And what that really means is, when can I start live streaming customer system data into some RAG solution to start pulling insights from that data? And I can tell you it's in development, it's on the way. Like many of us saw yesterday in the RAG workshop with John Willis, it really depends on what your data is and what questions you're trying to get out of that. So we're still developing that as we speak, and I'm really excited to see what comes next in the next generation of observability. I hope now you all are too. Thank you. Thanks so much.
Thanks, Wade. Great job. All right, our next speaker is Jessica Garson from Elastic. We had a really fun interview in the We Love Open Source studio yesterday, and this one should be fun as well. Here you are.
How's it going, everyone? So I typically actually talk about observability, but today I'm going to be talking about understanding vector databases. So show of hands of anybody who's ever heard of vector databases. Cool, most of you. And then how many people feel like you're an expert in vector databases? Raise your hand. All right, I'm only seeing a couple of hands. Cool. Well, for a while, I kind of thought of this as a buzzword, and now I've kind of learned some things about it. So, hi, I'm Jessica Garson. You can find me most places on the internet at Jessica Garson, and I'm a senior developer advocate at Elastic. And so when we think a little bit about what do vector databases do, I like to start with just showing an example of a very simple RAG application, or just kind of a generative AI application. And really, pretty much all of the generative AI applications that we've seen on this stage so far today have used vector databases in one way, shape, or form or another under the hood. But really, to put this into context, I like to start with kind of what we think of as traditional classic search. So when we search for things in Google, we typically just search, we say what we want, and then we get results back. But we're now moving more into a semantic approach. And semantic means not literal matches. So rather than list the keywords for everything you need, you're actually describing what you're trying to get done. And so one way I like to think about this is to think about Star Wars. So can anybody tell me what the well-known sentence of this scene in Star Wars is? Yeah, those are not the droids you were looking for. I heard a lot of people say it. So I'm going to talk a little bit about Elastic for a second. So if we look at a code snippet from Elastic's DevTools, this is basically our classic way of searching. We store some tokens, and then from here, we can actually kind of take a look at what's happening. So we added in an extra HTML tag to make it a little bit more interesting. But what it does is it is extracting the tokens and words that are most relevant and storing them. So from here, we can actually take out the HTML tags that we added, take out the period. From here, we can lowercase everything. And then from here, we could filter out the stop words. So we're down to droids you looking. And then we can use the snowball filter to take out the S and the ing, so we're down to droid you look. And so what's happening behind the scenes is that everything is inside of an inverted index, and it gets a start offset and an end offset. And the inverted index will have a list of all the tokens that it's ever seen, and that's what makes search so fast. It's token-based, and you could tune it through adding synonyms, tweaking queries, and that's really how search has been working for a really long time. And there's some pros and cons of this approach. The pros are that it's fast and scalable and easy to understand, but the cons are that you need to define synonyms, so you'd have to say machine equals droid. There's some issues with homonyms. It's hard to get image and audio search, and user intent is just really hard to capture. Also, it's really hard for question and answering, and for extracting meaning from longer questions. But it is very scalable and fast, and it works well for a lot of things, and it's been good enough for the long term. So this is where vector databases comes in. One, it allows you to implement a semantic search, and this allows you to kind of get that meaning from your text. And then also, it's really great for similarity searches for images, audio, and video, and it basically allows you to get relevant context of your data, relying on machine learning to encode your data and apply generative AI to create more human-like experiences. So that makes it a really great fit for RAG applications and other ML-type applications. So you might be wondering, Jess, what is a vector? And a vector, that is a mathematical representation of data like a word, image, or document as a list of numbers. So a vector database allows you to quickly find similar data through the use of vector embeddings, which is a form of vector data representation that converts words, sentences, and other data into meaning, or into numbers that capture the meaning and relationships. So really, they leverage a machine learning model to translate documents into numbers, allowing you to perform vector searches. So the way that I like to think about it is you have your images, your audio, your text, and you can use a machine learning model to add vector embeddings. And then from there, that gets turned into a vector representation, which is just a kind of an array of numbers. And then your query, that also gets turned into a vector. And then you can actually, or a vector representation rather, and then you can use a search, or you could run a similarity search such as approximate nearest neighbors to find the result. And that's really kind of what happens. So rather than just extracting tokens for search from one input type, you have various input types, and you can extract information through a machine learning model that represents what you have in an array of floats or bytes that you store. And really, this is just kind of the beginning of what you can do with vector databases. If you're interested in diving in deeper, all of the slides from today, all of my code that I've written for various different examples, this is typically a 45-minute talk, so there's different examples, different things like that that you can find, and I have some resources for further learning as well if you're ready to dive in deeper. Thanks so much for having me today.
Thank you, Jessica. All right, I know we're a little over on time. We've got one more talk, two great speakers, so thanks for bearing with us. Apologies for that. Arundeep and Dan, come on up. They're from Amazon Web Services, and please give them a warm welcome to the stage.
All right. Thanks, everyone. My name is Arun, and I'm a solution architect manager at AWS. I'm joined by Dan, who's on my team. Initially, I asked Dan to do this presentation, but he said, "Would you ever trust me if I went and did the presentation yourself?" I said, "No." So he's like, "Okay, let's do it together." And then we started, if I'm coming on stage, how many of you have heard the term vibe coding? That's a jargon right now that's running. I'm going to do something new, which is vibe presenting. This is a presentation that has been created in the last 24 to 48 hours, and I'm not kidding about that. So I put in the abstract into Claude Sonnet 3.7, and I asked it to generate a title for you. And it said, adaptive issue management through open source using domain-specific LLMs. I asked it to simplify it. It said, AI augmented open source issue triage management. I asked it to simplify it even further. It said, AI agent-driven issue management. And that's the original title which I had given to my talk. Now, there's a couple of disclaimers that I would like to add. These views are solely our own and do not represent our employers. And no LLMs were harmed during the making of this presentation. Right? So, as open source projects scale, what are the common problems that one might anticipate or see? These numbers are from VS Code, which is a popular open source project. And there are 31K forks of VS Code. And then there are more than 3K contributors to VS Code. But I'm really interested in the center portion of the slide, right? It has 8K issues, and it's trending upwards, right? 8,890 to be perfect. That's the data to impress your friend, right? But if you have a project that has these many growing amount of issues, how does one keep up in maintaining the project? As project maintainers, this is the biggest nightmare that one can have. And the problem is same throughout popular open source projects. You can see that the data in Flutter, React Native, PyTorch, any other open source project that you see, based on Octover's report, majority of the developers outside the organization where the project is maintained actually contribute by either creating an issue or commenting on an issue, or like some people like me who come and react to a specific comment on an issue, right? Now, as maintainers, we have a specific triage workflow that we use, right? A new issue comes in, and typically we spend about 5 to 10 minutes understanding what the customer is trying to do. And then what we do is we try to reproduce the issue in our local environment, and hoping that things are reproducible, we categorize that either as a bug or a feature request and have an SME from the maintainer community come and fix that for us. And if we need further clarification on the problem statement, then we usually go back and ask the customer for clarification questions, which usually takes about like 2 to 5 days. And eventually we write the final triage report, and then we come up with a response to customers on GitHub. Now, Dan and I maintain projects within AWS open source. We work on a couple of projects, Amplify and CDK, and we eventually modified the entire triaging process from this workflow to a newer workflow that Dan is going to talk about.
All right, thanks, Arun. Let's see. Okay, so with that existing workflow that Arun just described, it works for the most part, right? We're able to, respond to issues, but it does start bubbling up some issues that were evident to us. Really focused on frustration. So, for example, it might take a couple of days to really get to a solution, and so customers might get frustrated that, especially a high impacting problem is not getting addressed in time. There might be scaling problems where, because of the large number of issues that are occurring, we need to account for, hey, how do we need to get more people? Is that really the right approach? Is it scalable? That doesn't really work perfectly, as well as engineers and folks who are working on resolving these issues, and having to, spend time investigating, working on issues, potentially even spending more time on an issue that's not as high priority as an existing or a new issue that comes in later. So one of the solutions that we first started out with was automatic sentiment analysis. So essentially, a breakdown of this: as issues come in, we feed it through an AI-powered system machine, and that allows us to say, hey, this is a highly negative sentiment issue, and essentially escalated. And so that helped us in prioritizing. So, addressing high impacting issues that customers are raising faster, and allows us to, focus on the right issues. It also helps, tied to that, helps engineers address and focus, those high important issues. With addition to, with this new system, we don't need to have a dedicated person spending time with prioritization as well, or to at least meet the demands of new issues. So this is a screenshot. It's actually a live screenshot of the system that we actually do use today, and it just kind of highlights some of the, the view that you get by default. And so from this system, our goal was to essentially help with, the frustrations, the customer frustrations with, negative customer sentiment. But beyond that, we did start getting some benefits that, we started working towards, such as, it gives us feedback on what actually is working based on positive context, as well as, being able to integrate outside of GitHub as well, and be able to get historical context, which was actually pretty interesting because, for example, if the team releases a feature, a major release feature, for example, and we're able to track a period after that release, was there an increase in negative sentiment issues opened in the repo, or positive otherwise? So that helped us in addressing mainly the frustrated customers. But we also started seeing an opportunity to go beyond that, to help, especially with frustrated engineers who are spending more time on these issues. And so in a more recent addition to this feature, we took advantage of MCPs, which is, the latest popular craze, which is essentially, sort of new. And so what's happened with this feature now, as engineers are working in addressing these GitHub issues, they leverage Claude through MPCs to essentially, summarize the issue, highlight anything that needs to be highlighted without spending a lot of time, and also summarize what a fix potentially could be before we respond. And obviously, we're not allowing this to go rogue, do it on its own. We do introduce a human reviewer before we publish, and respond to the issue. And so what this has done, the benefit of this, has also tremendously reduced the amount of time that we spend triaging an issue.
So how did the new triage workflow look like? Once a new issue comes in, Claude does the analysis for us, which takes about like 5 minutes. And then it picks up the source code and analyzes the source code, which approximately takes 1 minute. And I promise that I'm not lying through the numbers on the slide. We have a human in the loop to review and validate the response before we send the response out to the customer. So the total triage time, as Dan mentioned, right, was reduced from over 50 minutes to 60 minutes per issue to 5 to 10 minutes per issue, right? And we actually had a success where a regression was caught in under 2 minutes. And you can actually see that how client actually brought the task that was at hand to analyze and triage the issue. And we immediately responded to the customer in less than 5 to 10 minutes, confirming the regression. And the fix was released in less than 24 hours, right? So the goal of our presentation was to make sure that we bring the power of agentic AI and MCPs. And rather than bore you all with the implementation details, we wanted to focus on the actual success and the metrics that we use to capture the success. And because I mentioned this was why presenting, I had an empty slide which I forgot to remove. Thanks, everyone.
Thank you, Arun and Dan. Thanks, everyone, for coming to the lightning talks. We're at time. Have a great day. Enjoy the rest of the conference. Please give all of our speakers another round of applause.